Hello, everyone. Here I want to show you how to solve 2023 AIME I problem 14. This problem gives us an analog clock with two hands, longer hand and a shorter hand. In each movement, we either move the longer hand or we either move the shorter hand. We cannot move both of them. So we try to move for 144 movements. So the ideal sequence of movements is that after 144 movements, so on the analog clock, there will be the 144 different positions of these two hands, right? So you want to go through all these different positions without staying at the same positions for 2 or even more times, right? So we call such a sequence of movements a feasible sequence. And after the last movement, you want to go back to their original positions. That is, both hands point towards 12. So how many such feasible sequences do we have? So although this problem is in the context of an analog clock, but first we'll have to convert it into a pure mathematical problem. So we may do the formulation in such a way. So let me use the notation x sub t and y sub t to denote the number of total movements of each hand after the t minus 1 total movements. Okay. So here, x sub t to denote the number of movements we make on the longer hand. And y sub t to denote the number of movements of the shorter hand. Okay. And we count up to the t minus 1 total movements. For each movement of a hand, its value is increased by 1. Therefore, we automatically have the condition that xt plus yt is equal to t minus 1. Okay. All right. So let's next check the condition that when we say after some movements, so we cannot go back to some position we experienced in the past, what that really means. So let's first see the conditions that this is violated. And then while we're trying to find out the feasible sequences of movements, we should avoid such conditions to happen. So let's think about the following thing. Suppose we are saying that there are two movements, xt, yt. So those denote the movements after their joint t minus 1 move. And there's another tuple called xs and ys that denote their respective movements after their joint x minus 1 movements. Suppose that after their joint t minus 1 movement and after their x minus 1 movement, so they get into the same positions. What that means? That essentially means that xt is congruent to xs and yt is congruent to ys modulo 12. So basically, this should never happen, right? Which means that when we find a feasible sequence, we cannot have such things to happen. That is, there exists two times t and s, such that x and y are both congruent to each other at these two different points of times. Both are modulo 12. Okay? So let's further see that under what condition such relationship would hold. Okay? So don't forget the condition here. The sum of x and y is always equal to t minus 1. So actually, that will allow us to simplify the rest of analysis. we no longer need to have two variables, x and y. It is sufficient for us to just have a single variable, x. Okay. So for these two congruent equations, I'm saying that they are equivalent to the following two. The first one is not changed. For the second one, I can replace this with the sum of the first and the second one. So it becomes xt plus yt is congruent to xs plus ys. And I recall that xt plus yt is equal to t minus 1, and x plus ys is equal to s minus 1. So the second condition could be reduced to t is congruent to s. Okay. So basically, to avoid experiencing the same positions at least twice, so such conditions should never happen, right? And let's look at these two congruent equations. Actually, the very nice feature is it allows us to separate the total number of movements from the values of a particular hand, the longer hand x, right? So for example, for the second condition, it doesn't depend on the pattern of our movements. It just set the restrictions on times, right? Which means that you want to check whether two positions are the same or not. So the first thing you have to check is, so for each position, how many joint movements you have made. So if the total number of joint movements of these two positions are not congruent modulo 12, so you don't even need to further check about how many movements we have for each particular hand, say for the longer hand, right? Because their positions can never coincide. So to avoid the coinciding positions, the first condition is that their times must be congruent modulo 12. Okay. Given this observation, we further realize that it could be easier to write the sequence for x's not in a single dimensional array from x1, x2 up to x144. So it could be easier for the rest of analysis to write x sequence as a two-dimensional matrix. And this is the 12 by 12 matrix. Okay, so basically the first row corresponds to the original first 12 axis, x1 up to x12. And starting from the second row in this matrix, so they correspond to x13 up to x24, etc. Okay, so now let's see why the matrix representation would simplify the rest of analysis a lot. Okay, so let's look at these two yellow conditions. We know that they should never happen, right? So let's see when they could happen and how to avoid them. So for t is congruent to s modulo 12, by using the matrix representation, what that essentially means. So t can only be congruent to s modulo 12 if these two entries are in the same column, right? Okay, and next let's see that for two entries that are in the same column, say one is xi and j, the other is xi prime j. Under what condition that xt is congruent to xs modulo 12? So we know that they should have the same remainder divided by 12, right? But to avoid the yellow conditions to happen, so basically it says that for all 12 numbers in the same column, so you pick up any two, they cannot be congruent to each other. And we know that divided by 12, the number of remainders is exactly 12, from 0 up to 11. So this has the following important implication. That is, to avoid the yellow conditions to happen, then we require that for each matrix, for each column in the matrix, so all entries if you compute their remainders divided by 12, they must be a permutation of 0 up to 11. Sounds good? So this is a very, very important observation. Let me formally put it down here. So let me introduce the notation R sub ij to denote the remainder of the entry xij divided by 12. Okay. So to avoid coinciding with the previously experienced position, then we essentially require that for every column, let me call them column J. Okay, so the remainders for every entry in the column are R1J up to R12J. This must be a permutation of 0, 1 up to 11. Okay, so basically it says that if this permutation property holds for every column in the matrix, so for such a construction of the sequence of movements, we are guaranteed that for 144 total movements, we will not have two movements that leads to the same positions, right? So this is automatically guaranteed by such permutation condition. Okay, and next, let's see if there's something else that we have to figure out. Yes, another useful observation is here. So let's look at some special values or the special conditions for some entries in the matrix. What about the first one, x11? So that is the starting point, right? Before the first move. So basically, the longer hand has not made any movement yet. So its value must be 0. This is trivial. And then let's look at the last entry, x1212. So that is the value before the last movement. And this is what we know. So we know that after finishing the last movement, we have to go back to the original position. And for the original position, the longer hand should point towards 12, which means that for x1212, and based on that, if we make one additional movement, so we get a new x that must be a multiple of 12. And when we move from x1212 to its next position, for each movement, for each hand, its value is either unchanged or is increased by 1. So it leads to two different cases. So the last number, x1212, is either congruent to 0 or -1 modulo 12. So if it is congruent to 0, it means that the longer hand is already pointing toward 12. So in the last movement, you do not have to move the longer hand. You just rotate the shorter hand. For another scenario that x1212 is congruent to -1 mod 12, it means that here at this position, the longer hand points towards number 11. Then in the last step, we should rotate it to let it point toward 12. Okay, so we have these two different scenarios. But the good thing is, in the rest of analysis, we don't have to analyze both of these two scenarios. It is sufficient for us to just analyze the single scenario, say for x1212, that is the multiple of 12. Why? Because now I'm proving for you that these two different scenarios should have the equal number of feasible sequences. Okay, let's see why. So let me use the notation at sub 0 to denote the collection of all feasible sequences, which means the collection of feasible matrices, such that the last one, x1212, is congruent to 0 mod 12. Okay, and analogously, let me use s sub -1 to denote the collection of all feasible movement sequences such that the last entry is congruent to -1 mod 12. Okay. So I didn't write down their definitions in the rigorous way because that requires me to write lots of things. But hopefully you get the key point about their definitions. Okay. So now I'm claiming that these two sets contains an equal number of sequences. To show their same cardinality, then we have to introduce a mapping function from S0 to S-1. And we have to show that this is a bijective mapping. Okay. So I define this function in the following way. So let's consider any matrix X or any sequence of movements in S sub 0. Okay. So this is how the function works. So for each entry, I and j, and I map its value to the following one. Okay. Oh, there's no F anymore. Yeah. So for each sequence in S sub 0, and you will check out every entry. So then I compute its functional value as this one. So then all these functional values will form a new sequence. I'm claiming that this new sequence actually is a feasible sequence in S sub -1. And also this is invertible, right? So you can show this is a bijective mapping. Although it seems to be very sophisticated, but the idea is very simple. And recall from our beginning that we initially introduced the two variables, x and y. They are used to denote the number of movements of the longer and shorter hands, respectively. Because they are subject to the joint constraint that their sum must be equal to t-1. So that's why we throw away y. But here for this mapping function, so actually what we essentially do here is we just swap the longer hand and the shorter hand. Just imagine that we still have y here. So basically it means that for each x, we, after applying the function f, we get its corresponding y value. So we just swap the longer hand and the shorter hand. That's it. This is very basic, right? Because you can swap these two hands. So of course, this is the bijective mapping. Okay, so that is the intuition. Although when we write it down here in the mathematical way, it seems to be complicated, but the intuition is very basic. So that allows us to establish the fact that the cardinalities of these two sets are the same. So in the rest of analysis, we just focus on one scenario. Say, let's focus on this scenario that x1212 is a multiple of 12. Okay. All right. So next, let's try to explore some additional structures of the matrix X. So recall that we have shown that one condition the matrix needs to satisfy is for every column, all entries, if you look at the remainders divided by 12, they should be a permutation of 0, 1 up to 11. And then I'm claiming that we have the following very important observations. So let's look at one column, say column J, where J is from 1 up to 11. So it's not the last column, okay? And let's look at its right neighboring column, J plus 1. So this is what we know. For every entry here, say for instance xij, when we move it to its neighboring entry xij plus 1, we know that this denotes the number of additional movements for the longer hand. So in each movement, either the longer hand is moved or is not moved. So the difference of these two neighboring entries must be equal to 0, or 1, right? It's very basic. And we know that every column has 12 numbers. So we have 12 such movements. So we can compute 12 such differences, right? And every difference is 0 or 1. So now the question is, how many combinations of such differences do we have? So although it seems that every difference for each row, it seems to have the binary values. So the total number of their combinations is 2 to the power of 12. But that is not correct. The answer is very simple. So to get a feasible sequence of the movements, we require that their move from a column J to its right neighboring column must be a synchronized movement. What a synchronized movement means? It means that either all entries in column J are increased by 1, or all entries in column J are not changed when we move to column J plus 1. So we call them the synchronized move. This seems to be a very strong property, right? So why it holds? What's the intuition behind it? So here, I will not give you the very rigorous proof, but let me just show you the key idea. And I believe that following this key idea, you're able to complete the entire proof, okay? So let's look at column J. Suppose that the synchronized movement property doesn't hold, which means that we have some entries here. Say, for instance, we have some right entries, and whose values are increased by 1. And for all the rest of entries, let me use green circles to represent them. Their values are not changed after the movement. Okay, so we have the mixture of 0 and 1. Let's see what is the contradiction. So let's look at those red circles, red entries. So we can compute the remainder of every red entry divided by 12, right? And among those remainders, so let's pick up the entry that has the largest remainder. So for example, let's say it's this one, the yellow one, that has the largest remainder. Suppose, let me give the numerical illustration. Say the remainder is equal to 7. Okay, so it means that the remainders of other red entries divided by 12 are less than 7. And also because 7 is the largest remainder among red entries. So that implies that, because we know for this column, so the remainders are permutations from 0 up to 11. So there must exist one entry such that its remainder divided by 12 is 8. But this entry cannot be red, and it can only be green. Otherwise, it violates our rule that we already selected the red entry that has the largest remainder, right? So it means that we can find a green entry whose remainder is 8. And now let's see why we get a contradiction. So for this yellow entry, because when it moves to the right neighboring column, its value is increased by 1. So let's look at the corresponding yellow entry in column J plus 1. So its remainder divided by 12 should be increased by 1. So it's increased from 7 to 8. Then what about the green entry? Recall that its remainder divided by 12 is 8, but its value is not changed when we move to the J plus 1 column. So its remainder is still 8. So now we get a contradiction, right? So we get 2 different entries that have the same remainders divided by 12. So this violates our condition that for every column, the remainders of all entries should be a permutation from 0 up to 11, which means that we cannot have two entries that have the same remainder divided by 12. Okay, so basically this finished the proof of this fact that when we move from any column J to its right neighboring column, we have to make a synchronized movement, which means that either all entries are increased by 1 or all entries remain the same. Sounds good? Okay. And before we do the formal counting, so we have to try to identify as many such key properties as we can, right? So the next very important observation is here. So recall that in this observation, so we talk about the movements for J that is up to 11, because for J that is equal to 12, that is the rightmost column. There's no way for us to move to its right. It goes beyond the matrix, right? But we still want to know about the properties of the rightmost column. So that is what I want to show you next. So for the rightmost column, we call that the bottom number. It's a sign because now we just want to focus on the case that is instead x of 0. So this is a multiple of 12, right? So we still have other 11 entries in the black circle. Okay. And let's look at the movement from each of these entries. So anyone could be written as xi, comma 12. So what could be the movement from this number? So when it's moved, so we cannot go beyond the matrix to go to column 13. It doesn't exist. So we have to go, say this is row I. So then the next row is I plus 1. So we'll have to move here to the first entry in row I plus 1, right? So the graph, so we are making the following movement, right? We move in this way. Okay. All right. So what is the properties that should hold in such a movement? I'm claiming the fact that these two columns are exactly the same. They're the same. You should not even have any movement. So we just copy paste their values from the upper right to the lower left. That's it. Wow, it seems a very strong condition. Why it holds? Here is the intuition. Okay. So let's look at the rightmost column. We know that the bottom number is a multiple of 12. So its remainder divided by 12 is 0. But again, we know that the remainders for entries in every column is a permutation from 0 up to 11. So we already have one that has remainder 0, which means that for the yellow section in the right column, so we cannot have any number that is a multiple of 12. But now I want to look at this particular number. Okay. So let me just zoom in. Say, I want to look at this particular number, whose remainder is 11. Okay. All right. So suppose its row is without loss of generality, let me say it's x5, 12. Okay. So we know when it moves to the first column, it goes here. That is x6, 1, right? On row 6. Suppose this red circle in the right column has remainder 11 divided by 12. So for such a movement, why I'm saying that its value cannot be changed or increased by 1. Its value remains the same. Because its value goes up by 1, then we know that the remainder of the entry x sub 6, 1 will be 0. But recall that on the leftmost column, the first entry is 0. So we cannot have another number that has the same remainder 0, right? So we get a contradiction. So basically, this explains that for the number on the right column, whose remainder is 11 divided by 12, when we make the movements from the right column to the left column, so its value remains the same. Okay? All right. So we are good with this entry. And then let's do backward. For the rightmost column, let's next look at another number that has remainder 10 divided by 12. Say this number is here. Okay? Suppose its position is x3, 12. So after the movement, so its r is equal to 10. After the movement, it goes here. The position is x4, 1, right? So why its value again should be the same? Again, we follow the same argument. Suppose its value is increased by 1. Because the blue one on the right has remainder 10, so its value is increased by 1. So in the left column, the blue circle has the remainder 11 divided by 12. But recall that the yellow circle has remainder 11. So then we get two numbers with the same remainders. So this violates the rule that it's no longer a permutation, right? So you see that if you make such backward induction, next you analyze remainder 9, 8, 7, etc. So you will see that to ensure that the left-hand side column is the first column is the permutation from 0 to 11. So basically, when you move from the rightmost column to the leftmost column, so all numbers should be the same. Okay? So this is the key idea of proving this fact. So far, so good? Okay. So far, we have disclosed lots of important facts, right? And let's see that by putting all these observations together, what kind of the structures we can find for this matrix. Recall that the first entry is 0, right? So let me denote by x sub 1, 12 as the last entry in the first row. And we just show that. So when we move from the rightmost column to the leftmost column, we just copy paste their numbers. Therefore, the first entry in the second row is still x1, 12, right? The same number. Okay, and next, let's apply the fact that when we move from one column to its right neighboring column, we have to do the synchronized movement. So by doing the synchronized movement, we know that the difference between all numbers on the left column and all numbers on the right column should be the same, because we are making the synchronized movements between any two neighboring columns, right? So what should be their difference? Let's look at the first row. The difference is x sub 1, 12. So it implies that the difference between any two numbers in these two columns that are on the same row should always be equal to x sub 1, 12. So this is a very important observation, because you look at the second row, the first number is x1, 12, and we know that when we move to the rightmost column in the same row, so the increment should also be equal to x sub 1, 12. So the value of the second entry in the right column is twice of x sub 1, 12. Okay? And let's continue. So it implies that the first entry, the third entry in the first column is x2 times x1, 12. And by adding the same increment, that is x1, 12, so we get 3x1, 12, etc. And you continue this process, the last entry is 12x1, 12. And you can see that it's automatically guaranteed that it is a multiple of 12. So this is a very, very important structure of this matrix. So the important fact is you look at the right column, okay? You look at the right column. So the numbers are multiples of some number called x sub 1, 12. And the multipliers are from 1 up to 12. So actually, this imposes a very strong requirement on x sub 1, 12. Why? It's because we know that all numbers on the right column, if you compute the remainders divided by 12, they should be a permutation, right, from 0 up to 11. So how we get such a permutation? Well, so it's the equivalent to require this number to be relatively prime to 12, right? So this guarantees that all numbers in the right column, if we compute the remainders, is a permutation from 0 to 11. Okay, so it helps us next to determine the values for x1, 12. Why? Because again, let's now go back to the first row. For the first row, we know that for each movement, right, between two consecutive entries, so the increment is either 0 or 1. And when we move from the first column to the rightmost column, the total number of movements is 11. So it implies that x1, 12 should take the value that is between 0 and up to 11. And also we know that it must be relatively prime to 12. So we know all possible values for this particular entry can only be 1, 5, 7, and 11. Sounds good? Okay, very good. So the next thing we need to do in our counting is, so let's look at the synchronized movements from each column to its right neighboring column. Okay. So here, from the leftmost column to the rightmost column, we have to make 11 such column movements. And for every movement, its value is either increased by 1 or 0. So now the thing is, we know for its 11 movements, and the total number of the value increment is just equal to x sub 1, 12, right? So we wonder that among those 11 movements, where the increment for each movement is 0 or 1, and the total increment is x sub 1, column 12, how many such column synchronized movements configurations do we have? So the answer is very easy. So among those 11 consecutive movements, we just need to pick up x1, 12 movements that has the increment 1, and the other movements have 0 increment. So the number of such arrangements is given by the combination number 11, choose x1, 12. Okay. So that denotes the number of feasible arrangements for the column synchronized increment. All right, so after identifying all these properties, now we are ready to get the answer to this question. So recall that we separate the entire sequences into two categories in terms of the remainder of the last entry divided by 12, right? And we have shown that they have the same cardinality. So we just compute this one. And for this one, we can do the computation in the following way. So first, we can do the casework analysis in terms of the value of x sub 1, 12. So it takes the value as 1, 5, 7, 11. For each given such number, then we count the number of arrangements of the column synchronized movements. So that is given by the combination number 11 choose x sub 1, 12. So we just compute this sum. And let's see what we get. So this is just a very basic algebra. The first number is 11. Next 11 choose 5. So this cancel out. Okay. So this gives us the value. This one, right? Okay. The next one is, so it's equal to 11 choose 4. So it's equal to this number. The last one, 11 choose 11 is 1. Okay. Let's see what we get. Yeah. So this is the answer. And this problem asks us to report the last 3 digits. So the answer is 608.